Have you ever wondered why galaxies from billions of years ago seemed to be bursting with cosmic rays far more than we see today? This question has puzzled astronomers for years, and the answer lies in a fascinating period of the universe's history known as cosmic noon. But here's the twist. Much of what we've learned about this era has been hidden behind something as simple as dust. Let's dive into the details and uncover how scientists are piecing together this cosmic mystery. Cosmic noon refers to an epoch that began roughly 2 billion years after the Big Bang, during which galaxies experienced explosive growth and rapid star formation. Imagine entire galaxies lighting up like fireworks, with stars forming at rates 10 to 100 times higher than what we observe in the present-day universe. These galaxies weren't just growing internally, they were also merging with one another, becoming more massive over time. Meanwhile, dark matter halos surrounding these galaxies were expanding rapidly, contributing to their evolution. For astronomers, understanding this phase is crucial because it sheds light on how galaxies grow and transform across cosmic time. But there's a catch. Observing this era isn't easy. Dust clouds obscure much of the visible light emitted by galaxies during cosmic noon, making it difficult to study them using traditional optical telescopes. That's where radio waves come in. Unlike visible light, radio waves have longer wavelengths that allow them to pass through dust relatively unimpeded. This unique property makes radio observations a powerful tool for probing the dust-obscured regions of the universe. By analyzing radio emissions, scientists can uncover hidden details about galaxies during cosmic noon. In groundbreaking new research, scientists analyze the radio-spectral energy distributions, SEDs, of 160 galaxies from this pivotal era. They use data collected by some of the most advanced radio telescopes in the world, including MeerKAT in South Africa, the Very Large Array in New Mexico, and the Giant Meterwave Radio Telescope in India. These instruments allowed researchers to separate radio emissions into distinct components and track changes in galaxy properties over time. The findings were published in the Astrophysical Journal under the title The Radio-Spectral Energy Distribution and Star Formation Calibration in Mighty Cosmos, Highly Star-Forming Galaxies at 1.5 less than Z equals 3.5, led by Professor Fatima Tabatabai from the Institute for Research in Fundamental Sciences in Tehran, Iran. According to the researchers, studying the radio SEDs of distant galaxies is essential for understanding how they assembled and evolved over billions of years. Most of what we know about galaxies comes from observing the light they emit, whether it's visible light or radio waves. However, visible light observations have limitations because they're often blocked by interstellar dust. On the other hand, radio waves provide a complementary view, revealing aspects of galaxies that would otherwise remain hidden. This realization inspired the team to conduct deep radio observations of specific patches of the sky using the MeerKAT telescope, located about 90 kilometers outside Carnarvon in South Africa. MeerKAT is a precursor to the upcoming Square Kilometer Array, SKA, one of the largest radio observatories ever conceived. As part of the MeerKAT International Gigahertz Tiered Extragalactic Exploration, MIGHTY survey, the researchers gathered simultaneous data on radio continuum, spectral lines, and polarization. This approach allowed them to measure star formation rates and probe the magnetic fields of galaxies throughout cosmic history. Our previous studies of nearby galaxies showed that radio signals between 1 and 10 gigahertz serve as a reliable indicator of star formation activity, explained Professor Tabatabai. Building on this knowledge, the MIGHTY survey extended their investigations to 160 early galaxies during cosmic noon and beyond. Their detailed analysis revealed that the radio spectra of these galaxies evolve alongside their star formation rates, a discovery with profound implications for our understanding of early star-forming galaxies. One key measurement in their study was the synchrotron spectral index, a parameter critical for understanding both cosmic rays and galactic magnetic fields. Synchrotron radiation occurs when high-energy electrons spiral along magnetic field lines, emitting radiation in the process. Interestingly, the researchers found that the synchrotron spectral index flattens with increasing redshift and star formation rate. In simpler terms, this means that galaxies during cosmic noon emitted proportionally more high-energy electrons compared to lower-energy ones. This finding suggests that cosmic ray electrons were significantly more energetic in the early universe, likely fueled by the intense star formation activity during that time. However, this raises an intriguing question. If cosmic rays lose energy quickly due to synchrotron radiation, how did these early galaxies maintain such energetic particles? The answer may lie in the nature of their magnetic fields. Highly tangled and turbulent magnetic fields could accelerate cosmic rays to higher energies, proposed Professor Tabatabaei. In such environments, cosmic rays scatter and decouple from the magnetic fields, allowing them to retain more energy. If this hypothesis holds true, then galaxies during cosmic noon must have been surrounded by vast halos of high-energy cosmic rays. The researchers also noted that the infrared radio correlation, IRRC, an indirect method for estimating the SED of distant galaxies, remains constant with redshift, even as the SED itself evolves in radio waves. These cosmic ray halos might explain this phenomenon, offering yet another piece of the puzzle. The implications of this research extend far beyond cosmic noon. It demonstrates that radio observations are incredibly effective at tracing star formation in the distant universe, particularly at high redshifts. With the Square Kilometer Array set to begin operations soon, astronomers will have unprecedented opportunities to map billions of galaxies and explore the ancient universe in greater detail. Our work will benefit greatly from future SKA surveys, which will enable more robust SED analyses in larger and more complete samples, the researchers concluded. So what do you think? Does the idea of turbulent magnetic fields accelerating cosmic rays challenge your understanding of galaxy evolution? Or do you believe there's still more to discover about this enigmatic period in cosmic history? Share your thoughts in the comments below. We'd love to hear your take.